This conference will now be recorded.
Okay, thank you, Martin. If you can present.
Brilliant. Afternoon, everyone. It's nice to see so many people. I had no idea that we get so many people to a seminar during the day. That's really great. It's pleasing to see everyone's so focused on keeping their CPD up. That's really good. I'm Martin O'Connor. I'm the Principal Route Engineer for Electrification and Plant for the Northwest Route of Network Rail. I've spent most of the last 20 years in various electrification roles, from working in design offices, working on site doing construction, and most recently being in the asset management team in the Northwest. I was looking back in my diary the other day when we were preparing for this session, and I realised that I presented something very similar alongside John Fry in Manchester to the PWI in April 2005. Today I'm joined by Gareth Morgan and Ashleigh Turner. Gareth is a project engineer in our electrical safety improvement team who's delivering various overhead line and conductor rail projects to try and improve our compliance with electricity at work regulations, and also trying to get us to a place where we can take isolations in a different way and hopefully more efficiently in future. Ashleigh works in my team as an asset engineer. His role predominantly is speccing up future work, understanding the asset condition information that we've got, and helping to build plans for the future. So today, the presentation, I think Dave gave a reasonably good overview of what we're going to try and cover. The title was a little tongue-in-cheek conversation between me and Dave Brooks. Dave knows that I'm quite keen on listening to music and making music, and he contacted me one evening asking for a title for this presentation, and I fairly flippantly said, "Above Us Only Wires," and many people will probably recognise the line from a famous John Lennon song, "Above Us Only Skies," and it just happened to stick on this occasion. So we're going to try and take you through some basics about the overhead line system, try and look at how it interfaces with the permanent way, and also have a look at some of the things that may happen if we get it wrong. So if we could go on to the next slide, please, Gareth. Cheers. They've given me the easy bit at the front end because they know that I don't spend as much time doing this stuff as I used to. What I'm going to first of all do is just try and give you an overview of the sort of basic components. So the title of the presentation, "Above Us Only Wires," as we all know, it's not quite that simple. It's not just some wires. And this diagram here shows a headspan type structure that actually we don't favour these days. Headspan structures have been quite problematic for us over the years. And as you can see, well, I'm going to talk you through some of the things you can see on the screen here. But the main sort of factor as to why we don't really like headspan structures is that if we have a failure on one of the 4 tracks shown there, it will impact all 4 lines, or there's a very high risk of it impacting all 4 lines, and we like to have each line mechanically independent. But what you can see there in this, if I work my way through sort of in order of the numbers, and then maybe we'll talk about a little about each as we go. So number 1 being the catenary wire. A lot of people refer to overhead line as catenary, and actually the catenary wire, it's because it's a catenary system, and if you think about sort of geometry, the overhead line system is a catenary system. and some people do refer to it as that. But the along track conductor, called the catenary, is the conductor that everything else along track hangs from. So you can see that coming from item 1, the catenary, we have droppers, and the purpose of the droppers is to hang the contact wire, which is item 3. And the contact wire is the conductor that the train's pantograph is in contact with. On this particular example of the headspan, you can see that we've got multiple wires that go between the 2 masts across the tracks, and they have different names, and they form this headspan structure, and they all have slightly different purposes. I won't go into a lot of detail, but you can see that we basically have a top span wire, which we've called the headspan wire here, and some cross span wires. And the cross span wires have some of those wires are live and some of them are not live. From a PTS and personal safety point of view, you would want to be assuming that everything up there is live, obviously, and you wouldn't want to be going within 2.75 meters of it without an isolation. But you can see quite clearly there that the insulators, marked as number 7, are doing 2 things on this headspan. They're keeping different tracks apart, so each running line on there, this is probably up, down, slows and fasts maybe that we're looking at here, each has a different electrical section, and I think later on one of the guys will run through a bit more on that. Not everything's all connected together, and the simple reason for that is that when we have a fault, we don't want everything to go off. We don't want to have all trains on all lines stop if we have a circuit breaker trip. So you can see across the span wire, the insulators are keeping the different tracks apart. They're also keeping the live equipment, or the equipment that's at 25,000 volts, away from the equipment that is earthed or connected to traction return. So you can see the example here, the top 2 wires that form this headspan have got no insulators between them and the masts, and that's a really good indication that they're at earth potential or connected to the traction return system. You can see also that we have a structure number plate on there. It's really important from a safety point of view that we know these overhead line structures have unique identifiers, and if there is a problem or a fault, we need to be able to get to the structure. We know where it is, or if we're taking an isolation, we need to know where the isolation starts and ends, and where it's safe to work and where it's not safe to work. So structure numbers are really, really important piece of safety information, as well as a piece of asset management information. And you can also see some additional along track conductors. They're marked as number 10. Now they can be different things and installed for different reasons. And some examples of that, we could have earth wires that are just used to connect all of the structures together to minimize the number of times that we need to connect to the rail. We can also have return conductors that look quite similar sometimes, but they're on smaller insulators. We also now have in the auto transformer system conductors that are along track feeders. So they are 25 kV conductors on full size insulators, and they provide part of the 25 positive, 25 negative system that we use to space our feeder stations further apart and get more capacity on the system. So if we go over to the next slide, please, Gareth. Just a few facts and figures. The nominal system voltage, 25,000 volts, 25 kV in the UK. You will see systems light rail systems that have a lower DC voltage. Our system now is all 25 kV AC, 50 hertz system. That's the supply frequency in this country. Every train, electric trains running on the system tend to draw between 200 and 300 amps. Our standards cap single train current at 300 amps, but we do have some exceptions. For example, an 11-car Pendolino will pull about, I think it's 307 or 309 amps, and there is a derogation in place to allow that. Nominally, there's about 50 kilometres between our feeder stations, and the feeder stations at the point at which we bring an external supply in from either National Grid or the distribution network operator onto the railway. We have other sites in between those feeder stations that are there for the purpose of voltage regulation, paralleling sections together, and also operational reasons and switching. We have something called the neutral section, which is usually located at the midpoint between two feeder stations. With an AC system, the supplies are, I should have given you something visual here, but they're basically a sine wave. And if you think of this sine wave as the supply, if you derive the supply from two different sources, the sine waves will be out of phase from each other. And it's really important that we keep them apart. So we have a special type of insulation, which is basically two lots of insulation back to back almost, with an earth section in the middle that provides that separation and makes sure that we don't damage trains or equipment by drawing arcs between the two different phases. So that's the electrical side. Mechanically, most of our systems are auto-tensioned, and depending on the equipment type, that can range from 9 to 16 kilonewtons. We do have some fixed termination equipment where the tension will vary depending upon the temperature. We generally try not to install new fixed termination equipment, with the exception of we would probably do it if it were a new depot or at sidings, but other than that, on the main lines we try to avoid it. It's also quite a maintenance burden having fixed termination equipment. Typically, the tension length, as we call it, the point from the balance weight or spring tensioner to the balance weight or spring tensioner at the other end, is typically 2 kilometers. That will vary significantly in different places, but we're just short of 2 kilometers is a typical tension length. We've got a couple of different types of contact wire that we generally use in the UK. There are a few exceptions, but most of, say, the West Coast Main Line will have 120 contact wire, with us having some 107 contact wire when we get into our equipment that hasn't been upgraded, our Mark III equipment that we've got in a few places still. A lot of our contact wire, or all of our contact wire, is copper based. Copper's got some really good characteristics, particularly its ability to carry current. Its conductivity is really good, and typically the pantograph exerts a force of about 90 newtons on the contact wire. That's really important that that's maintained around that level, because it's one of the ways that we try to minimize sparking and arcing, which ultimately damages pantographs and damages equipment. We try to design a system that gives us as near to sparkless current collection as we can achieve. And just a final mechanical point there, the system is designed to deal with wind and ice loading on the conductors to varying degrees of success, I would add. So I'm now going to hand over to Gareth for the next few slides.
To me, to Ashleigh.
To Ashleigh, that was
yeah.
organised, wasn't it?
It's fine. So I'm just going to talk about some other elements related to the overhead line that we've got. For example, the traction power system itself. So this is essentially the schematic here is showing the flow of the power distribution from our feeder station to the train and back, because as with every electrical circuit, it needs to be a complete circuit. So we start with the transformer at the feeder station on the top, which, following the red arrows, you can see goes onto the catenary system and contact wire. From there, we go through the pantograph of the train, where it goes through the motors, and that useful energy is used to propel the train. From there, we still need to have that return circuit. So typically the way is using the steel wheels themselves to create an electrical connection to the running rails, where we utilize one of the running rails as our return path. From there, we have features known as red bonds, highlighted red because they're an important feature, because they are what are completing the circuit. Without these, we can have the overhead line fail, or the power distribution side of it fail. These red bonds connect that track to a return conductor, which is running alongside the track. It's one of the along track conductors, which ultimately then returns back to the transformer at the feeder station. Other things that we may have around here is something known as a return screen conductor. This is ultimately there to reduce any EMC, electromagnetic compatibility issues, which predominantly will cause issues on the signaling and telecoms cables, and may cause wrong side failures of that equipment. Moving on to the pantograph and contact wire interface that we've got. So as mentioned before, we have the contact wire where we essentially is our power delivery point for providing to the electrical traction trains. To receive that on the train itself, we have a pantograph which has a horizontal component to it known as the pantograph head. It's important, as Martin mentioned before, that we maintain a good contact with this. So there is a 90 newtons upwards force which is maintained by pneumatically operated pantograph system, which in itself also allows for damping for when the contact wire moves up and down vertically. In more modern pantographs, we have something known as an ADD, which is an automatic dropper device. These typically are pneumatic tubes that run in the very top of the pantograph head, that the moment that they are ruptured, the pneumatics in that system is released, and the way the pantograph will work is that it will automatically drop because the pneumatic system no longer has its pressure, so it can't maintain the height. Other things to note is that any incorrect installation or alignment of the overhead line can very much affect the overhead line geometry here. So if the contact wire, was too far to the side of the pantograph, we will typically get a failure mode known as side wear, which is an accelerated form of wear on the contact wire, which typically leads to premature failure and dewirements, which are not so great. Which leads nicely onto safety. Although I'm looking at safety in a different point of view here. So one of the reasons, well, one of the difficulties in using AC is alternating current, is that the electricity itself can quite easily jump to other features, including humans, if they are in a position where they are standing on the ground and earthed. It's obviously weather dependent, so more humid climates, you need greater separations to ensure that safety. And what we've come to in the UK particularly is two different requirements on distances for, well, safe distances. One of those is, as shown on the left diagram, is for public areas on number 1, which is a 3.5 metre distance from a standing surface. So it's important to note that this is to any of the electrical equipment. So it's not only the contact wire, but it could be any part of the overhead structure that is oversailing a platform. So for example, seen on the picture on the right, to the left of the insulators, you can see that there are live parts of that cantilever frame still over the platform. It's important that 3.5 meters is maintained, which in this particular instance, it has not been. The one reason for us working with 3.5 meters here is that the public themselves are, of course, unknowing of the risks of electricity, so we have to give them a greater clearance. But also we've got to consider other factors, such as the fact that they may be carrying something such as an umbrella, which increases it reduces their distance to the live equipment. Other cases may be next to footbridges, for example, where we've got to, again, maintain that clearance, in this case, a 2.25 metre distance to said equipment. On the flip side, the workforce is still the 2.75 meters, as has always been briefed at PTS, and that'll be a shorter distance because of we're made aware of those risks and constantly reminded of it in our life-saving rules. So I don't think I have anything more on this one, Gareth, if you want to move on.
Okay, thank you very much for that, Ashleigh. Hello, everyone. So now I've put together a few slides which really cover the relationship between the overhead line and the track disciplines and things we should do really to work together better. So I'll go on to the next slide. There you go. So the first aspect I want to cover is the height of the overhead line system, and more particularly the height of the contact wire. So ideally, the contact wire height would be constant throughout the entire railway system. So this is so we can maintain contact between the pantograph and the contact wire. That uplift force, that 90 newtons we've talked about, would ideally be the same the entire time, and this would reduce wear on the system. If we think about High Speed 1, the UK's purpose-built high-speed railway, the contact wire height only varies vertically by 1 centimetre throughout the entire route. This is because High Speed 1 was purpose-built for electrification. Therefore, any bridges over the railway line are high enough to have the clearances required, and there are no level crossings on the route. At level crossings, we've got a minimum wire height requirement of 5.8 metres, and this is so to ensure vehicles can pass safely underneath. In some cases where we've got an overbridge, so that's a bridge which crosses over the railway line, the contact wire is as low as it possibly can be, and so are the electrical clearances between the overhead line equipment and the bridge. In these circumstances, it's not possible to raise the height of the track. Because of the clearances we have, we can't raise the height of the overhead line any closer to the bridge, and therefore we limit ourselves to the height of the track. In these circumstances, if we think about track maintenance, we won't actually be able to permit any track raising such as tamping, so this can make track maintenance in these areas much more difficult. If we stick with the theme of bridges, if I can get the next slide. Wiring through overbridges can be very challenging. The railway in the UK was built, from the Victorian era, and electrification hasn't necessarily been around since then. The way to get overhead line through bridges, there's a couple of techniques that we use. Ideally, we'd use a free running system. This is where the overbridge is high enough that the overhead line can free run, so the wires can freely run without being attached to the bridge structure itself. This is because the underside of the overbridge is high enough that we have the electrical clearances required. In many circumstances, our Victorian railway system, we don't have these clearances. In these cases, we have to register. So registration is where we hold the contact wire to limit it in a horizontal plane. And so the contact wire is registered underneath the bridge itself. We use special registration arms called underbridge arms in these circumstances. And these limit the amount of uplift of the overhead line equipment to maintain the clearance between the bridge and the contact wire. The first thing we need to do when electrifying a low overbridge is to think about how we're going to fit the wires through. If we look at the bottom diagram here on the screen, the first thing we do is we reduce what is called the encumbrance. The encumbrance is the height difference between the contact wire and the catenary wire. So looking on this bottom diagram, the flat line at the bottom is the contact wire, the vertical lines are the droppers, and the top wire is the catenary wire. As we can see, nearer to the overbridge, the droppers get a lot shorter and the encumbrance distance is much smaller. In some circumstances, the contact wire and what is essentially the catenary wire are at the same height to fit under the bridge. To manage this, what we do, we splice out a section of the catenary wire around the bridge area, and in its place, we splice in a section of the contact wire. Then as both of these contact wires run underneath the overbridge, they both come into contact with the pantograph. So this is known as twin contact or contenary. So as well as reducing the encumbrance, the other obvious thing we need to do is reduce the height of the contact wire itself. To do that, over many spans, we need to gradually grade down the contact wire height so it falls naturally from the usual height of the contact wire to the reduced height underneath the overbridge. The main way to do this is to use the actual weight of the system itself to naturally fall down under gravity. So we're not forcing it down using registration arms, which can lead to excessive tension in the system. It's important to note as well, the contact wire height gradient directly impacts the pantograph speed due to the amount of wear that can be caused on the pantograph and the overhead line. So if we've got a steeply graded contact wire, the 90 newtons uplift force will be exceeded as the pantograph is moving towards the bridge as the contact wire reduces its height. The gradient I'm referring to of the contact wire, as that has an impact on the wear of the pantograph on the overhead line system, that reduces the actual line speed of the route in these areas. This can be particularly challenging where we have an overbridge and a level crossing in close proximity. So the overhead line height needs to go from the high level crossing height to clear vehicles to the low height throughout the bridge. So we have quite a steep gradient, and there are locations in the UK where line speed has been limited because of that. I just go on to our next slide. So to prevent the contact wire wearing a massive V-shaped groove in every pantograph system we have in the UK, we stagger the contact wire from side to side. If we look at this photo here on the bottom right, this is the top of one of the pantograph carbons. So carbon is normally used as a strip on top of the pantograph because it can be easily replaced but also conducts electricity well. We can see the clean scraped area across the entire width here where the contact wire has moved side to side as it staggers along. To maintain stagger, we use two types of cantilever structures. We use push-off cantilevers, and these are where the contact wire is being pushed off the structure, and we use pull-off cantilevers, and this is where the contact wire is being pulled towards the structure. If we look at this photo down here on the bottom left, I can't demonstrate with a pointer, but if we look at the nearest cantilever to us on the left-hand corner, we see here the contact wire is being pulled towards, so that is pull off, yep, so the contact wire is being pulled off towards the left. And if we look at the track on the right, the contact wire is being pushed off, so pushed away from the cantilever towards the 6-foot. As the cantilevers are opposite each other on a 2-track railway, we normally have alternative push off and pull off. So this is so the contact wire of the 2 tracks zigzags in parallel down the straight. On the next span along, so the next structure up where we can see where the train is, the pull off and the push off reverse. So this is what maintains the zigzag stagger down the straight. On curves, it's a little different. On curves, usually we position the structures on the outside of the curve, and we pull the wire off the center line of the track, and this is to overcome the radial loads of the overhead line system. One of the key considerations with stagger is if we want to slew our track. So for any reason we wanted to move the track from one side to another, or maybe change its alignment, we need to be very careful that the position of the pantograph doesn't move so it comes off the side of the contact wire. A couple of issues we'll have here. First of all, if the contact wire moves away from the pantograph head, we might have arcing and loss of contact. This means the train will lose power. It also means the arcing will damage both the overhead line equipment and the pantograph. Also, it's important to maintain the contact tension throughout the system. If the pantograph moves too far to the side away from the overhead line, the corners of the pantograph are actually, if you see the profile, it hooks down, and that hook can hook over the top of the contact wire or either of the wires and actually force it down and cause the overhead line equipment to be pulled down, and that's what we call a dewirement. So another area which is quite critical really is switches and crossings and how we electrify them. So usually for a crossover, as the bottom left photo here demonstrates, we have an extra wire run. So this is demonstrated here as yellow. So this extra wire run is quite short and is usually used just to wire the crossover itself. At one end we have a fixed termination. So this is where the contact and catenary wires are fixed via an insulator directly to the structure. And at the other end we will have a balance weight or a tensioning device to maintain the tension for the crossover. The contact wire of this crossover wire run actually runs above the contact wire for the main line. So this, therefore, if a train was charging down the main line, which is indicated here by the red contact wire, the pantograph wouldn't actually come into contact with the crossover wire. So this reduces wear on the overhead line system and prevents wear on the crossover wire. Obviously, if the crossover has not been installed correctly and the contact wire height is below that of the main line, a pantograph of a train racing down the main line could snag the contact wire of the crossover and cause damage, excessive wear, forces on the system, and eventually a dewirement. It's important with switches and crossings that the contact wire is held in a very specific place. As we've got a diverging line, we need to make sure that the pantograph constantly maintains contact with the contact wire. The way we do that is at a set of points, there's a very specific location where we need to register the contact wire. This location is where the main and diverging lines, where the running rails of those is 200 millimeters apart. There's a handy guidance table, which I've put here on the right-hand side from the track design handbook, which shows us the distances from the toe-off point to that structure for different types of turnouts. So that leads us on to a consideration of changing turnouts. Maybe we want to do a line upgrade and we want to change the speed of the turnouts to be higher speed turnouts, so they're more gradual. We might want to completely remodel a junction. So that means the turnouts themselves will need to change. Any change to the track geometry such as that means we need to realign the overhead line equipment so it perfectly matches up with the track geometry. And if we're moving the overhead line equipment, there's a very high likelihood that the structures that support the overhead line will be in the wrong place. So new structures might need to be required and redundant ones removed. I think that quite nicely leads us onto a couple of examples of when things perhaps don't quite go so right for overhead line equipment.
So you may or may not have seen these videos before because they're quite well known on YouTube. This first one is showing something, showing a failure when the equipment, when an equipment of the overhead line has failed, but the pantograph has kind of maintained a contact. So initially, an electrical contact is maintained throughout. So the driver is unaware, he doesn't know that a failure has occurred. And as you see, the train continues to move. Later on, the train then meets a turnout where we've got a new wire run coming in. With the pantograph now askew and not in its correct orientation, it actually snags the overhead line from that wire run, and essentially it begins to then pull all the equipment down, as you saw. Only then does the train lose its electrical connection, and only then does the driver know something is probably wrong. All being told, all of this damage is over 1 kilometre of damage from the point of initial impact to the point where the train finally comes to a stop. And just let it finished. So this is a failure of what happens when we don't have the automatic dropper device, the ADD, as I mentioned before. This second video is a much better story. Still a failure, unfortunately caused by an overhead line failure again. Something hanging off a registration arm that shouldn't be there. But as seen at that impact point there, the pantograph automatically fell down. And as you see, the contact wire is still very much still up in the air. So we haven't, there may be some damage on that one structure, but instead of 1 kilometre of damage, we only have perhaps 1 or 2 spans of damage at the most. And I think that leads us on nicely to questions.
Okay, thank you very much for that. There is a couple of questions in the chat. If anyone has got some questions, if you can go on the chat bubble and put some questions in there. The first one is from Patrick Dickinson. It's is the switch toe opening dimension measured when the points are set to normal? Is the question from Pat.
Do you want me to that? So if you look at where that measurement's taken in the track design handbook, it's not. It doesn't matter. It doesn't matter at the point that measurement's taken.
Okay, that's great. There's one that I might have asked, but this we'll see how this one goes. So Jerry Manley's asked the question: what's the presenter's views on voltage control clearances?
Okay, this is a brave new world for us, this one. Voltage control clearances is absolutely, it's an essential sort of piece of work, and all the principles and technologies that have been brought together to allow us to reduce clearances is essential if we want to make electrification work in the future. I think that when we look on a location by location basis, we have to make sure that we consider all the factors when we apply voltage control clearances. So for me, that's things like looking at every discipline, getting them to understand the constraints it will place upon their maintenance. It would also be making sure that we'd understand what we would do if the voltage control clearances were not a successful solution. So what I mean by that is these voltage control clearances and the principles that have been developed are meaning that it's basically big pieces of civil engineering work that we're now not doing because we're reliant upon these principles, and we can't fix them overnight. If we find that we have a problem, then we have to understand what the fallback will be. So sometimes there will be additional maintenance tasks that we have to do to maintain them. Sometimes we might actually be having to ask ourselves the question that if we are right on the limits of what we believe is acceptable, do we need to have an operational fallback where if the clearance was ever compromised, or we couldn't maintain the clearance for whatever reason, that we'd understand operationally what we do. Now, on a route with bi-mode trains, for example, that might not be a big deal. We could have an on-the-shelf design ready to go where we fit balisers for pantograph lowering and raising as a contingency. But on a route where only electric trains operate, that side of it could be challenging. So maybe that's answered. I hope that's answered your question. But it's quite a brave new world to us, and we're really bought into it because we know the future of electrification, really, or additional electrification, and the network rail decarbonisation strategy, the traction decarbonisation strategy. It's really important that we make this work.
Okay, thank you, Martin. That's a comprehensive response to that. Please forgive me to get the name wrong. So as noted, what are the presenters' views on using BSN 50119 grading rules instead of network rail grading rules as per NR 27715 for contact wire?
So we've quite actively, well, in the Northwest, I can only really speak for the Northwest, but we've quite actively done this as part of the Northwest electrification programme, and in line with the introduction of GLRT 1210, which was a really big, it seemed like a very big challenge, a big thing for us. It introduced some clearance requirements in public areas and some differing requirements at overbridges. Now, as part of doing the risk work associated with that, one of the things, or one of the compromises that we made, was to look and to actually implement grading that was aligned with the BSCN rather than the network rail 27715. Now the BSCN is less onerous. We looked at line speeds and we applied the BSCN where it was appropriate to do so in order to increase the clearances. So we're open to it, but it's always looked at on a case-by-case basis.
Okay, great. Next one is from Mike Evans. How big is it? How big a challenge does line side third-party vegetation present?
Oh, okay, yeah, it's a constant, ongoing challenge, and again, speaking from our personal experience in the Northwest, there's an ongoing program that tries to maintain the vegetation clearances line side, and there's a wider program that's looking how we prevent that longer term. So my colleagues in this sort of off-track world are looking at making clearances that basically project vegetation clearances that project that 45-degree angle from the track to try and head off our vegetation issues, we then will try to maintain it at that. But it is a real challenge. It is a difficult challenge for us. And third-party vegetation, it can take us many months to negotiate with a third party to remove a tree. For example, we've just undertaken a sort of a pilot on a section of West Coast North, where we've been looking at what the constraining factors were and why we put a blanket emergency speed restriction on in high winds. And as we work through this exercise, as we work through it, we had the RSSB involved, looking at non-EMP factors, non-electrification factors in this that were limiting the speed of trains, or led to us to limit the speed of trains. Now, part of that, we did our own vegetation work, but we identified over 100 third-party trees that we needed to remove in order to reduce the risk, to the point where over that section we were able to not impose a blanket speed restriction at the same using the same criteria. So it's a real challenge, and particularly third-party vegetation is difficult for us. It's quite time consuming.
Okay, thank you. Maybe a couple more questions now. Just there's one from John Lipscomb. Why does heavy rail use very high voltage AC systems, but light rail use low voltage DC systems? With a lower voltage, could we presumably reduce clearances and make electrification cheaper?
Lower voltages are great for light rail vehicles. When as an example, if we think about Metrolink, I notice Pete Summers is on there. Feel free to join in. Metrolink, as a light rail system, they're light vehicles. They are located in areas where we would probably have a greater challenge to maintain the clearances, particularly, and also with lower voltages, we need to draw higher currents from the system. So if Metrolink tomorrow bought a new fleet of heavy vehicles, which is highly unlikely, I guess, but if they were to buy heavy rail vehicles that require much more current to get them moving, we'd need significantly more power supply intakes, much heavier overhead line equipment, and actually it would probably make the overall cost much more expensive of new electrification if we had to electrify the low voltage DC system, because that's another factor. Our substations, we talked about sort of 50 kilometers apart. If we look at one of our DC systems, and okay, not an overhead line system, but Merseyrail, our DC substations are much closer together, and that would drive cost into a new electrification scheme. Also, with DC systems, we tend to experience much higher losses, electrical losses.
Okay, yeah. I was just going to squeeze a couple of, there's some comments. And Pete Summers is saying hello, Martin, and things like that. I was just going to do a vote of thanks. Before I do that, I'll squeeze in a question for myself. What's your biggest challenge from a climate change perspective, Martin, going forward from an OLE discipline?
So I think the main one for overhead line, from my point of view, is that we've experienced some real warm weather in the summers the last few years. Maybe not quite so bad in the last 12 months, but the year before we had some real problems with that. And I think that one of the biggest challenges will be the fact that we've got quite a bit of fixed termination overhead line equipment that I mentioned at the start of the presentation, and that's equipment where when it gets warm it starts to sag, and that's when we start to have problems. That was designed for a temperature range that if we were able to go in and frequently retension that equipment, or much more frequently than we were able to, then we could probably keep it going. But as we get to these higher temperatures, the sag in that type of equipment has caused some significant disruptive failures. So a big area would be to get rid, where possible, of all of the fixed termination equipment that is on main lines. I think we can live with some risk when we get off onto sidings and depots, but eliminating fixed termination on main lines is a real big thing for us.
Okay, thank you, Martin. I think I'll just bring we're closely coming up to 2 o'clock now, so if I can just ask for people to unmute, and I'll just do a quick vote of thanks. Thanks to yourself, Martin, Ashleigh, and Gareth. That was, for me, as a track discipline, it was really, I think I've got a better idea of what I'm looking at when I am looking above these days after your presentation. So I think it's going to be a useful point of reference as well for others if we can put this on the PWI site. So I was going to ask, I don't know if people can be unmuted, and then we'll just do a unmute all. Can I do that?
Thanks a lot, guys.
Yeah, just a quick round of applause. Thank you.
We've had a virtual round of applause before. Thank you. Thanks for having us here.
Pete Summers with a hairstyle I don't recognise.
Been growing a bit, Dave, over lockdown, yeah.
All right. Thank you very much.